Okay, so hello everyone. Welcome to this special colloquium at ICTS, a special online colloquium. So it's a great pleasure to have our speaker, Siddhartha Mishra, today. He's a professor of applied mathematics at ETH Zurich in the Department of Mathematics. He's also the director of the Computational Science Zurich and a core faculty member of the ETH AI Center. So a lot of us know Siddhartha Mishra from his research interests in numerical analysis, specifically related to computational fluid dynamics, but also in various complex systems. Of late, many of us have followed his work talking about machine learning, neural networks, and that'll form a bit of the talk today. So Siddhartha Mishra is a renowned applied mathematician. He's won a lot of prizes. I'll just mention a few. So he was, I believe, the 2015 von Mises Prize winner, the Jacques-Louis Lyon Medal in 2018, and of course, the Infosys Prize winner in mathematics in 2019. This is an exciting talk about some exciting areas about the intersection of PDEs and neural networks and deep learning. So we look forward to that, and I'll hand it over to Siddharth, please.
So thank you very much, Vishal, for the introduction, very kind introduction, as well as for the invitation. I'm delighted to speak here, and let's get started right away. So now, of course, it's okay. I believe you can see my slides. Okay, some people say that we are living in the age of machine intelligence because intelligent machines or intelligent algorithms assist us in so many aspects of our life, whether it comes to translation or facial recognition, and increasingly in the sciences and in engineering, for instance, this famous work on protein folding by the team in DeepMind. And sort of the central characters in this saga are deep neural networks and big data, the availability and the presence of big data. The question that I'm going to ask and trying to answer today would be, can deep learning have a similar impact on scientific computing like it has on several other aspects of human life? And in particular, I will stick to my expertise, which is models, physical models that are described by PDEs or partial differential equations. So I'm talking to an audience of physicists with some mathematicians thrown in, so I don't have to tell what a partial differential equation is. Needless to say, all that I want to say is that if you want to model anything from the subatomic sort of elementary particle scale all the way to the scale of the universe, you need PDEs or partial differential equations. So at the level of atoms with the Schrodinger's equation, stars, the global climate, and even morphogens in living tissues, various things are modeled by PDEs. And the issue with the PDE sometimes is that it's very difficult, except in very special cases, to find analytical solution formulas. And so what we do these days is that we solve PDEs on a computer. We simulate them on a computer. And to do this, we use what are called traditional numerical methods. These are methods that have been developed in the last, let's say, 80 to 90 years to approximate PDEs using a computer. And they come by different names. So you have finite differences, you have finite volumes, finite elements, collocation, spectral methods, and so on. This is for the spatial discretization, and for temporal discretization, whenever you have time-dependent PDE, we use different flavors of Runge-Kutta algorithms. And I'm not going to give you a talk about traditional numerical methods, but I just want to sort of try to revisit what a numerical method does, because this will be pertinent to us in a few minutes. So let's take some examples of what a numerical method can do. So this is a traditional, very standard elliptic PDE. Some people call it as a Darcy flow. So you have a PDE which looks like this. This is the divergence operator. This is the gradient. U is the solution of the PDE. F is a forcing term, or source term, if you want to call it. And A is some sort of a coefficient. So depending on the application, it could be the conductance if you are looking for the temperature, so you're solving a sort of a steady state diffusion problem, or it could be the permeability if you're solving a sort of a Darcy flow steady state pressure problem, whereas U is the temperature or the pressure, and you are interested in solving this problem. So what is the input to the PDE? Assuming that the forcing is known, for instance, an input could be the permeability field. So this is the rock permeability, which is the input to your PDE, and your output is going to be the solution of the PDE. So this is a sort of, this is the input, this is the output. So what this traditional numerical method, in this case, the finite element method, you could also use finite difference methods, does is that it approximates the so-called solution operator. So solution operator is a mapping between one infinite dimensional space and another. So that's what an operator is. So it's input and output infinite dimensional objects, functions in this particular case. And so what it does is that it approximates the solution operator. So this is pertinent to what we're going to discuss about. Similarly, let's take a slightly different, more complicated model. So now we're talking about fluid flows. So you can think of the compressible Euler or compressible Navier-Stokes equations, whatever fluid model that you like. And so here is an example where given the initial density, velocity, energy, or momentum for that matter, what we want to predict is what is the value of these objects at a later time. So the input is the initial condition, another function. The output is a very complicated function because this is a complicated flow. So as a consequence, you will have an output. But remember, it's the same paradigm here. So the numerical method, in this case, a finite volume method developed in my group, what it does is that it takes the input, which is a function, and it provides you the output, which is another function. So again, we are approximating operators. So the key message here is that numerical methods, they actually approximate operators. And they're very successful at doing that. Means even in my lab, we have solved various problems with these traditional numerical methods, whether it comes to core collapse, simulating core collapse supernovas, whether it comes to simulating stratocumulus clouds, sort of rock slide generated tsunamis, flows past rockets, very, very complicated flows, and they have been very, very successful. So why not stop here, right? So why we don't stop here is because there are some serious issues with these traditional numerical methods. And the main issue, in my opinion, is the computational cost. These solvers, this PDE, the traditional numerical methods are very expensive. They're so expensive that they make certain problems infeasible. The problems that we want to study, they're not feasible because of the cost of these methods. Just to give you an example of what sort of costs we are talking about. So especially for what are called many query problems, where instead of solving a PDE once, you have to solve it multiple times. For instance, if you want to do uncertainty quantification, if you want to design, which is very important in engineering, if you want to solve an inverse problem, in all these problems, you have to call the PDE solver again and again and again. And this becomes very expensive. Just to give you an example, so here is an example of a flow, a compressible fluid flow, which is solved using or approximated using a code developed in my lab. And this is a very sort of complicated flow. It's sort of very small scale features. The point is that for a single simulation, for a single realization of this flow on one of the state-of-the-art supercomputers, it's 15th in the top 500 at the moment, PSDAINT. This is the one that we access here in Switzerland. And the simulation, this takes, it's 1,000 cubed simulation. So you have 10 to the power 9 degrees of freedom per time step. It takes 300 node hours on a supercomputer. It doesn't sound like an impressive number, but the point is it is. And the reason is that a single sample or a single realization of this fluid flow carries very little information because it's chaotic, it's turbulent. So you have to do it time and again if you want to get the transient behavior right. So to compute the statistics, you have to repeat the simulation with slightly different realizations, let's say 500 times. And that is costing you approximately $1 million to do this. And now imagine in all supercomputing centers in the world where we are doing these kind of physics simulations, how much of energy and how much of cost we are spending, how much of expense we have. And this is why we cannot do certain things. For instance, we can only do 500 samples. We can't do 5,000, or we can't go to 2,000 cubed and do 5,000 samples. So there is a limitation that the cost puts on us. And one of the reasons why this happens is because, in my opinion, traditional PDE methods like finite difference, finite element, these are what are called data agnostic. So there is some discussion that I have in this paper. What do I mean by that? So now we will come back to this picture many, many times. So this is the sort of data physics landscape. So here is physics, so which is given by your PDEs, ODEs, and so on. So here is the physics. And what traditional numerical methods do is that they use a lot of physics. You need all the physics in order to do these simulations, and they don't use any data. They're data agnostic. They don't take care of data. So we don't really sort of access the entire data physics landscape. And this gives you suboptimal results. So the question that I'm going to ask and trying to answer is, if I combine physics with all the data that is getting available to us these days and all the data that has been around, can we improve the situation? Can we make these methods scale? Can we do problems that at the moment are extremely expensive? Can we do that at scale? Yes, and the answer to this would be a qualified yes. That's the sort of rationale for my talk. And let us try to walk you through the steps to do that. So let me recollect the setup a little bit. So again, as I said, PDEs are sort of associated with PDEs that are the solution operators. So let me start with an abstract PDE. So this is an abstract PDE. You choose your favorite PDE. Could be Navier-Stokes, could be elliptic equations, whatever you want. So this is a solution of the PDE. It takes some input, source or initial boundary conditions. It has some coefficients. So this is the input. And the input to output, they live in this Banach spaces X and Y. So these are infinite dimensional. And it's important to remember that associated with this Banach spaces, there is a probability measure because we are going to sample from a certain probability measure. So the point is that, so this is the most general setting where we would like to be. However, this is very hard because it's an infinite dimensional setting. So because our mapping that we're interested in approximating is a mapping from a Banach space to another. And this will be formidable. I'll come to that in the latter half of my talk. So I'll start with the simplified setting, which is seems a big limitation. It is a big limitation. Nevertheless, there are many, many problems that correspond to it. And the limitation that I'm going to make is that the measure that I'm taking, the infinite dimensional problem that I'm interested in, is actually a finite dimensional one. So my inputs are actually finite dimensional. My output could be infinite dimensional. So this is a sort of a serious restriction. Nevertheless, it is satisfied with a lot of PDEs, what are called parameterized PDEs. Let me give you an example just to illustrate that. This example comes from aerodynamic shape design. So you have an airfoil. In 3D, this will be the wing, but I take a cross section of the wing, the airfoil. And what I'm interested is in shaping the airfoil so that certain aerodynamic parameters, mostly the drag, is going to be minimized for constant lift. And I'm going to look at a sort of a search space, a shape space, and I have parameterized the shape with finitely many parameters. So in this case, 50 parameters typically. So I parameterize them. So my measure is restricted to a measure on 50 dimensions. So 50 parametric dimensions. And my flow now is a function of time. It's a function of space. And it's a function of this parameter space, which is 50 dimensional. And I'm going to search for the optimal shape within this parameter space. So I've simplified my problem a little bit, but as you can imagine, many, many problems in engineering have this kind of parameterization because you need to manufacture this airfoil or this wing at the end. And for each realization of this parameter that corresponds to a certain shape, we're interested in the sort of long time flow or the steady flow. So it looks something like this. It's a compressible flow. So you have some shocks and some smooth regions and so on. So this is the setup. You could be interested in the solution field as a function of space and time, or you could be interested in certain observables like the lift and the drag. So these are some quantities of interest, some functionals of the flow. And these are the objects. So at the moment, if you use traditional numerical methods, so for each realization of the shape, these parameters, I have to do a CFD simulation that takes me approximately half an hour in 2D, and in 3D, much, much more, very expensive. And then I do my optimization. So this is going to be rather expensive. So what I'm going to do is I'm going to approximate this for these parametric problems. I'm going to approximate the fields or the observables, so whatever we are interested in. And I'm going to approximate them with these deep neural networks. As I said, these are central players in machine learning. So what are deep neural networks? I assume that these days everyone knows what deep neural networks are, but just to fix ideas and to fix notation, I just recall what they are. So in this setup, for me as a mathematician, deep neural networks are just functions. So they're functions which map one finite dimensional space to another. So the input is going to be a vector. The output could be a vector. It could be a scalar. It could be a probability. It doesn't matter, but it's always a vector to a vector or a vector to a scalar map. And this mapping, it's a composition. It's a composition of what are called elementary functions or hidden layers. So you take an input vector, you put it through the first layer of the composition, then the output, you put it through another layer of the composition, another layer, and so on. So you concatenate the compositions, and the elementary function or the hidden layer has very simple pieces. So it has an affine piece. So you're given a vector, you transform it, you multiply a matrix and add another vector. So you have an affine transformation. And then you add a scalar nonlinearity, or you compose it with the scalar nonlinearity. So the scalar nonlinearity could be what are called activation functions, ReLU, tanh, and so on. And this is inspired roughly by how neurons in our brain function at that level. So that's why they're called neural networks. And the training parameters, so the tuning parameters, so these are the functions, these are parameterized functions, and the parameters are given by the weight matrices and the bias vectors. And the point is that these maps or these realizations of neural networks, we're going to use them to learn the target function. Now, the target function, of course, you have to provide some input for the target function, and this will be provided in the form of training data. So we will we'll look at this finite dimensional domain, could be a very high dimensional, 50 dimensional domain, let's say, and then we are going to choose some random training points in that domain. We have to provide the values, the ground truth, possibly noisy, but let's look at the noiseless case. And I'm going to adjust my parameters of the neural network so it fits these values. So that when I have a new value of the parameter space, it's a continuum. So I have a new value, I can match it. So this is roughly the idea. So this loss function, as you can imagine, this is non-convex because we have this compositional structure. So you have to solve a non-convex optimization problem in very high dimensions because this theta, these weights and biases, they can be hundreds of thousands of dimensions, millions of dimensions, but these days increasingly trillions of dimensions. So this is a non-convex optimization problem in very high dimensions. So you have to use some stochastic gradient method. But this is what training with neural networks really boils down to. Given data and given an architecture, which is how many layers, what is the type of activation function, and so on, you can do this. You can sort of train neural networks to recover the target function that you have. So now remember that my objective was to sort of find or approximate my fields, observables corresponding to parametric PDEs with deep neural networks. So this is the algorithm. The question is, can this be done? Means, okay, can any arbitrary function be learned by these neural networks, be approximated by these neural networks? And the answer to that is a resounding yes. And the reason for that is because neural networks have a very nice property, theoretical property, that they are universal approximators. So if you give a target function which is measurable, this is as less regular or as little hypothesis as you can think of. Certainly continuous functions are measurable, so they are included in that. But many other discontinuous functions also belong to this measurable category. Any integrable function is measurable. So within this category, there exists a neural network. In fact, a shallow neural network, one hidden layer is sufficient so that you can approximate it as accurately as you want. So in principle, yes. So we can learn any of these functions by neural networks, which is great. But this does not tell you a lot of quantitative information because you want to know how big the neural network is, how many samples you need, and you want to answer this kind of quantitative questions. And to that end, you need to do a little bit more math. So it turns out that the total error, which is the difference between these two, has three pieces. There's one piece, which is the training error, which is associated with the solution of this optimization problem. That is difficult to estimate, but the other two pieces can be estimated. The approximation error, that tells you what is the best approximation error. That depends on various hypotheses on your target function. In particular, it depends on how many derivatives exist, how many derivatives make sense. The size of the neural network scales in this manner. So it depends on the regularity of your function, how many derivatives are there, and it depends on the dimension, how big a dimension space you're drawing from. So the problem here is that if you don't have a lot of regularity, if you, let's say the regularity is 1 or 2, then you end up with what is called a curse of dimensionality. So this means that it will take larger and larger networks to approximate functions. So 50-dimensional function will become very difficult to approximate. The first set of non-trivial mathematical results that one can prove is at this level, that because PDEs have a lot more structure than an arbitrary smooth function or an arbitrary CS, continuously differentiable function, we can prove for a variety of PDEs, and there are different groups in the world which have done that, that this size estimates or the approximability is not exponential in dimension, but it's rather polynomial in dimension. And not just polynomial, these are rather small polynomials. Means they could be like, even in the extreme cases, it's quadratic. So it's linear, quadratic. Some cases it's even logarithmic. So in principle, very small neural networks can approximate these objects, solutions of PDEs efficiently. So these are the first sort of non-trivial mathematical results. That gives you one piece of the error. But there are other pieces of the error. For instance, what is called the generalization error, which comes because you are taking an integral here. So the error is an integral. But here, as you can imagine, sorry, I need to go further down. Here, as you can imagine, we are replacing an integral with a quadrature. So we are going to make some quadrature errors. And this is where you use some statistical learning theory, and one can prove results like this, which tells you that this error depends on the size of the neural network, but more importantly, it depends on a square root of the number of samples, which is okay when you have lots of data, because if you have, let's say, 100,000 or 1,000,000 data points, then it's okay because the error is going to be small. But in many applications in scientific computing, data, you don't have as much of data, because generating data is either through numerical simulations or through experiments. And numerical simulations, as I just told you, are expensive, but experiments are even more expensive. Just try to go into a wind tunnel and do some experiments. It's very, very expensive. So this is why we have to remember that unlike in sort of face recognition or speech recognition, something where you have Wikipedia and you have lots of image databases, we don't have that much of data. So in a relatively data poor regime, we have to do this process by using only 100 to 1,000 data points. We can't use 100,000 or 1,000,000 data points. So the square root here is not a good news for us. So in fact, some of the first works that we did in my lab is to somehow use numerical analysis, because numerical analysis, traditional numerical analysis, gives us a whole bag of tricks on how to deal with this problem. So one has to adapt them, one has to modify these ideas, and this will help us. So the first thing is that unlike in traditional machine learning, the data is usually something that is given by the user, either through simulation or through experiment. In either case, we have the freedom to design which points we're going to sample from. So instead of taking random points, which are sort of all over the place because they're random, you can use what are called low discrepancy sequences, which are better distributed. Just to give you an idea here, so you can, I've just taken a square, I've broken it down into small squares, 25 small squares. And if you look at the random points, which are the blue dots here, many of these small squares don't have a single random point. Here there is not a single random point, at least in this particular realization. Whereas you can design some other points, for instance, Sobol points or low discrepancy sequences, which are better distributed, while still not incurring the curse of dimensionality, or only incurring a mild curse of dimensionality. So then one proves that in that case, the 1 over square root of n that we had here, which was bad for us, is 1 over n now. Okay, there's a logarithmic correction, but it's 1 over n. So this is one of the tricks that one can use, but there are many different tricks, multi-level training, and so on. I don't want to spend too much of time on that. But the main point is that because numerical analysis gives us a bag of tricks, we can both reduce the approximation error as well as this generalization error. We can learn with a few samples. So let me give you some examples, because I want to talk about some other more interesting things. So one of the examples is you can do predictions now. So I like this example because this is something very fundamental in what I do. So you are interested in this flow past the airfoil, right? Steady flow, because you're interested in cruise conditions. So this is how your density looks like. So there's a parametric problem with, I think, 20 parameters in this particular case, or maybe 50 parameters, I don't remember. And so you are interested in this kind of a flow. And what we do is that we are predicting the whole flow. We are predicting things like the drag and the lift. And we do so with only 128 samples. So this is a challenge, right? We don't have that much of data. We want to do it with 128 samples. And we have relatively small networks, because this is what we have proved, right? That small networks suffice. So our networks are like 10,000 parameters. So these are small networks, easy to train, easy to evaluate. And the main point is that these are high resolution simulations. So it took about 40 minutes. Maybe you can do it in 10 minutes, but it's of the order of several minutes to generate each of these samples. But it's fast to train these networks, and the evaluation is lightning fast. So if you're interested in just the lift and the drag, it takes 10 to the power minus 5 seconds. Even for the whole flow field, it takes 1/5 of a second. So remember, we have 30 minutes and we have 1/5 of a second. So you have 3 to 4 orders of magnitude speed up with small errors. So this is the promise of neural networks, that they can do. So if I just use traditional numerical methods, it will take me forever to simulate. But with a trained neural network, and the training time is not that long here either, it takes me no time to simulate these things, provided that I have, means I use small amounts of data. If I need a lot of data, I would have just done my simulation. So this is the important thing that one has to remember. One can also do time-dependent problems. So here is a simulation of a time series generated by a tsunami. So we have a tsunami of the coast in the Mediterranean, off the coast, there's an earthquake of the coast of Crete. And then we are measuring in off the coast of Italy, off the boot of Italy. And you can see that we do a very good job at the time series. Again, this is a parametric problem because the seafloor deformation, this has been, people have worked for 50 years and they've built a very nice parametric model called the Okada model. And if you do a sort of physics-based simulation, which we did in my group also, it took about 60 minutes. So 1 hour for the entire simulation. This is the state of the art. However, with neural networks, you can do sub-second. So again, you can do 2-3 orders of magnitude. You can do sub-seconds and errors of approximately 1%. So in these kind of problems with these tricks, we can do quite a lot. And we can use these trained neural networks, these surrogates, which are emulating the numerical method. We can use them, for instance, to do uncertainty quantifications. So instead of having a single realization, you're predicting statistical quantities. For instance, the PDFs of the probability density functions for the lift and the drag. You do it very accurately. And now this is because it also means you have to be very careful how you measure the speed up. So if I just had Monte Carlo, which is not state of the art here, you get enormous speed ups, like 3 orders of magnitude or 2.5 orders of magnitude. But even with the state of the art, you get 1 order of magnitude speed up just with plain vanilla neural networks. And then if you use multi-level training, you get another factor of 5. So overall, you get approximately a factor of 50, which makes these problems feasible, particularly in 3D. You can also do shape optimization. This is the problem that I originally started with. You need another twist. You can't just use plain vanilla neural networks the way I just described them. You have to do what is called active learning. So there's some interaction between the training of the neural network and the optimization process itself, the shape optimization process itself. This is in this paper here with some colleagues at the IFR. And as you can see, we were able to reduce the drag by 50%, which is also done by traditional numerical methods. But the main thing is the advantage in cost. So this is how a traditional numerical method did this problem. So you needed up to 4,000 or 3,000 to 4,000 evaluations in order for the forward problem, in order to get these kind of low errors. But now we can do it with 60 evaluations. So again, you get a factor of 50, factor of 60 speed up in this entire process. We can also do Bayesian inversion, inverse problems in this kind of a setting. So it's very, very successful. But there is a big caveat here. In addition to the caveat that I needed a good parameterization, because without a good parameterization, you are lost. But in many engineering problems, this parameterization is available. Now,
can I ask a question?
Yes, absolutely.
Siddhartha, can I ask a question?
Yes.
It's an obvious question. I mean, why does this work?
Yes. So why does this work is contained in some of these theorems, right? Because so the first thing why it works is, so this is the error. Okay, there is, of course, the training error is, this is, I have no estimate on it, but you can monitor it. But these two pieces of the error, we can prove even for these problems that this is going to be small. This is only going to, the neural network need not be very large, which is the case in these problems. And second thing is this piece of the error, by using these Sobol points, I've said that it is 1 over n. So it's sort of it's a linear decay in the number of samples. So if you have 100 samples, this gives you approximately 1%, right? And the other thing also gives you approximately 1%. So a priori, you know that your error is between 1 and 2%, and which is where you are. So you are able to prove also in this particular case that these functions are such that neural networks can approximate them efficiently with low data. So we can prove that, but we also demonstrate that empirically. So in these particular cases, that is the advantage here is that the neural networks are very good at approximating these kind of functions. If you want to ask a sort of a first order answer, but that's what is happening under the hood. Of course, one can prove some rigorous error estimates. But as I said, there are some caveats, which I'm going to explain in a minute. Are you satisfied with the answer?
Yes, I understand actually that inequalities are very important to prove.
Yes, this is very important here. So without these, if I just use things naively and don't use this special structure, then it is not going to work. So remember that again, I come back to this data physics landscape because this is very, very important. So what I described to you, so traditional numerical methods here, all physics, no data. Now we have a moderate amount of data, but we don't really use the physics at all. Means I don't use the physics whatsoever in these particular problems because I've been given data generated by some numerical simulations, and it so happens that the neural networks are very good at approximating these objects with less amount of data. This is what it is. But now the caveat is, okay, you needed moderate amounts of data, but here most of the data has been generated by simulations. And this requires PDE solvers, which can give you a reasonable computational cost. Means already in 3D, this will be very, very difficult. But actually, even in 2D or in many, many problems, you might not be in the situation where you can get even 100 or 1,000 data points. And these are problems with complex geometries, where it's difficult to generate grids, multi-physics systems, and especially PDEs in high space dimensions, because these are grid-based methods. So as soon as you go to high spatial dimensions, not parametric dimensions, spatial dimensions, then you can't do this anymore. So I'm talking to physicists. So you have Boltzmann equation, which is high space dimensions, radiative transport, and so on. There are many, many problems which fall into this category, Black-Scholes, Schrodinger, and so on. So supervised learning does not work in this setting. We have to do something unsupervised. Unsupervised means we don't have any data or very, very less amounts of data. Instead of having 1,000 data points, you have 10 or something like that. And there are mechanisms by which you can do this. One popular mechanism these days is what is called physics-informed neural networks. I did not invent these. These have been around now for quite a while. But what we have done is mostly try to understand why these physics-informed neural networks work. Maybe I'll try to explain this a little, because this is very important these days. So the idea is that I want to solve a PDE using neural networks. Okay, let's take the heat equation in space-time. So we have the heat equation. I take zero boundary conditions. So this is time out here. This is space. So 2 dimensions in the space-time domain. And you have zero boundary conditions out here. And you have some initial conditions. And you want to solve this problem. Of course, for the heat equation, you can write down an analytical formula. But I can make it very easy to not be able to write down an analytical formula. So what you can do is you can use a traditional finite difference method. This is what I teach in my basic numerical methods for PDE courses. Let's say that we don't know anything about finite differences. We never knew anything about Taylor expansion, because finite differences is Taylor expansion. We only have neural networks. How are you going to solve this problem? The answer is that we can solve it, and we can solve it very, very easily. So I will allow, so I'll have neural networks. So at each point in space and time, I have a neural network theta, which is parameterized by a parameter vector theta, weights and biases, and this will give me a value, okay? And now what I'm going to do is, within the class of neural networks, I'm going to find the best representative that is going to solve the heat equation. That's all that I can do. And what's the information I've been given? I've been given that I have some boundary conditions, initial conditions. So when I evaluate it at 0, then it should minimize the mismatch here between the initial conditions and what the network produces. I have some boundary conditions, 0. So I just want these guys to be as close to 0 as possible at the boundary. And in the interior, I don't have any data, but I know the PDE. And the PDE is the heat equation. And here, given a neural network, remember that this is a function of space and time. So these are its inputs. We have automatic differentiation, something called backpropagation, which is sort of the backbone of all neural networks, which allows me to evaluate the time derivative very fast. It allows me to evaluate the first derivative in space and the second derivative in space very fast. So I can form what is called a residual, PDE residual, and I'm going to minimize this. So I'm going to put all this information into a loss function. So I want to find a neural network such that it fits the initial and boundary conditions as well as possible, while at the same time minimizing the PDE in this sort of pointwise strong sense. And this, as you can see, is highly scalable. Means it can be scalable in terms of course, I have to do it I can't do it in a continuous manner. I have to do it at a set of collocation points, which I can choose randomly. So I can go high in dimensions because I can always take random points in 100 or 1,000,000 dimensions, no problem. And you can do it in principle. And I can also scale it in terms of PDEs because nothing here told me that I can't take nonlinearities, or I can't take third order derivatives, or I can't take a space-time derivative. All of these can be available from automatic differentiation. So that's why it's a very, very simple method. And so now I just minimize. So my minimization problem is a tad more different, right? Because you have this PDE residual instead of just minimizing some data. And you can do that. It's one reason why these things. Yes.
Siddhartha, I have a question.
Yes, please.
So you said you minimize pointwise. So what about
Yes.
solutions that are discontinuous?
Yes, I will have some explanation about that. You came
Okay,
to the point
okay.
very quickly, but I'll come to that. Maybe I don't have a slide,
Sure,
but I
sure,
can
sure.
discuss that. But anyway, so now we are assuming that some regularity is there. So the first thing is that it's very, very trivial to program, right? So this is all the code that you need to solve the heat equation. It takes 3 lines of code. So that's why it's very, very popular. And the second reason why they are great is because there is quite a sound theoretical basis now. It's primarily from my lab, but from other people also. And this is a question that I think Vishal asked, which is that if your PDEs are regular, if the solutions are smooth enough, then one can use sort of neural network approximation theory to say that this residual, this object that you are minimizing, these objects are going to be small enough. Because otherwise, what's the point? We're trying to minimize something that will be of the order of hundreds of thousands. So the fact that your PDE solutions are smooth is very important, very germane to the fact that you have some control on the residuals. So that's the first thing. But this is only true if you have sort of global minima. If you have local minima, then you need to show that the total error is small. Here we use some properties of PDEs, means the fact that PDEs are coercive or sort of stable. And there is a rich theory, there is a deep theory. And the point is, as long as for a large class of PDEs, as long as your solutions are smooth, we can actually prove that pins are able to sort of approximate the PDEs quite well for forward problems as well as for inverse problems. I have an example for inverse problem in a minute. And it also explains the limitations of pins. For instance, if the solution is going to be discontinuous, then they are not going to work so well. And there are some fixes for that because you have to use a weak formulation and so on, but not in this strong formulation. Anyway, this works quite well. For instance, let's take linear parabolic PDEs, so-called Kolmogorov PDEs, which are the Kolmogorov equations correspond to stochastic processes. Now, heat equation is an example of that. Black-Scholes equations from options pricing is an example for that. I'm running a bit out of time, so I'll rush a little bit here. So the main point here is that you can prove as well as experimentally show that these pins, this completely unsupervised approach works. So you use some deep math here, Dinkin's formula and so on, some representation formulas for the solution, and then you are able to prove the results that you want to prove. And let me just show you this example here. So different types of Kolmogorov equations, heat equation, Black-Scholes, Heston, and you can solve a 100-dimensional PDE with 1 to 2% error, and you can do it like in 10 minutes on a GPU. So this is no data is necessary. It's a completely data-free. It's unsupervised. So that's one of the advantages. And you can do it for more sort of physics equations, right? Like radiative transfer. All of you should know that to solve radiative transfer has been an industry because people have different ansatz spaces, different kinds of representations, because it's high dimensional. In the most general case, it's 7-dimensional or at least 6-dimensional, right? It's hyperbolic, it's sort of mixed type and so on. You can apply pins, it works well. You have theory for it. And the interesting thing is now you can solve a 6-dimensional problem on the same GPU. And you take 1 hour. In the 2-dimensional problem, you have very low 0.3% error. But even in the 6-dimensional problem, you have like 2% error. So you can really, no traditional numerical method can do this, but this can be done with pins. You can, you can do solitons, solitons of different types, completely integrable equations. The main point now is that there are more derivatives, right? So this has 3, some of them have sort of non-local derivatives, fractional derivatives, and so on. So you can do quite a bit of different things. You can do sort of industrial scale problems. Here's an example. So you're doing additive manufacturing. So you have a nonlinear diffusion equation, which is parametrized. If I just used finite elements, it took 32 hours to sort of scan the search space, the parameter space. And with pins, you can do it in like 0.4 or 15 minutes roughly. So it's a really fast algorithm. So you have 2 orders of magnitude advantage. So here, again, if you go to this, and you can solve inverse problems, but maybe I just skip that. You can solve inverse problems because I want to tell some other things. You can also solve inverse problems because in inverse problems, you also provide data. So the data and physics come together to be able to solve inverse problems. So coming back to the data and physics landscape now. So remember that traditional numerical methods are here. Pins can be a replacement for traditional numerical methods, at least for some problems where And if you have some data, they can sort of supplement, but they need perfect physics. They need a lot of understanding of physics, they need the PDEs, otherwise you can't solve these kind of problems, even with data. Now, still a large part of this cartoon space for data and physics is still unexplored, right? And remember that there is a big caveat, and this is the caveat, that's why I sort of rushed through a little bit, because I wanted to explain this in the last 10-15 minutes that I have a little bit. So remember that we were always in this sort of parameterized setting, and we made this assumption that everything is sort of realized by a finite amount of parameters, and we need complete knowledge of the underlying physics. Otherwise, for instance, you cannot use pins. Now, in reality, this is not true. In reality, your physics is incomplete, it's missing. Maybe there are several parts of it that we don't know. Data is coming from observations, and you have no good parameterization. Some of these parameterizations that I talked about, for instance, in the tsunami problem, it took 50 years to build it. So for new applications, you don't have these parameterizations. So the point is that we have to go back to this original point that numerical methods were doing, which is that they were approximating the operator directly. Now, the question is, they were approximating this operator, solution operator, using physics. Now, the question that we're asking is, can we do it with data, purely from data, or as a hybrid between some physics and some data? And this is the sort of the topic of operator learning. And that's why I want to explain a little bit what it is and why I think that this is the sort of, if not the silver bullet, but it goes a long way in solving some of these problems that we are encountering. So let me sort of encapsulate what operator learning is. So remember that we have the PDE solution operator. So this is a mapping from a function to a function. So this could be the input to the PDE, and this would be the output, function to a function. And what we are going to do is we are going to build a surrogate, an approximation for this operator. But now we can't use deep neural networks just like that, because deep neural networks were able to take a finite dimensional input, a vector, and were able to produce a finite dimensional output. And we were able to manipulate that, to solve our problems. But now we don't have that. We have an input, which is a function, and output, which is a function. Input could be temperature over Bangalore today. Output could be the temperature over Bangalore tomorrow, right? So that would be what a weather forecast does. The question is, can we do this? And can we do this kind of an operator learning? It turns out we can. And one way to think about it is to revisit the traditional numerical methods, because they were doing this. They were taking inputs as a function, producing a function. So my reinterpretation, people who developed these algorithms did not develop them in this manner, but this is a good way to think about them. So remember that my operator is a mapping between one infinite dimensional space and another. But a traditional numerical method, what it did was to approximate this through these three arrows. So what you do is you are given a function, an infinite dimensional input, you project it down to a finite dimensional space. For instance, in a finite difference setting, you just take the initial data and you evaluate it on grid points. In a finite element setting, you project it onto a finite element basis, like a Colloquium basis, and so on and so forth. So this step is what I call as an encoder. So you take an infinite dimensional input and you project it or encode it in finite dimensions. Traditional numerical methods would do it in this manner. Once you have finite dimensions, you can manipulate it. So you use the physics in traditional numerical methods, for instance, to update it in time or to solve the finite element matrix problem and so on. So this is where the physics came in. This scheme is all based on physics, right? And finally, to go back to infinite dimensions, because we started with infinite and you want to go back to infinite dimensions, you, for instance, for finite difference methods, you use some sort of interpolation, let's say polynomial interpolation. For finite elements, you did what is called Colloquium interpolation. So you lift or reconstruct from finite dimensions to infinite dimensions. So this is what traditional numerical methods do. They project, encode, they do some approximation based on physics, and they lift to infinite dimensions. Now, the problem is that in the setting that I'm considering, you don't necessarily have the physics to do this, right? And B, you don't necessarily have all these polynomial interpolations, because then you'll be hit by the curse of dimensionality to do this. So how are we going to do this kind of a process? So it turns out that there are very neat results. There are very neat constructions, which, even though they were not designed as such, they fall into this paradigm. And there are two of these that I'll very quickly touch upon, and then I'll stop. So one is what is called operator networks. This was introduced by two computer scientists, Chen and Chen, in the 90s. And this has been extended by George Kanedakis and his group at Brown University. And let me just go to the main point here. So remember that I have this projection, approximation, and lifting, right? The projection is done by point-wise evaluations. So given an input function, you just evaluate it at finitely many points. You can think of these points as sensors. So you're measuring your input at finitely many sensors. You can also do sort of functionals, so that's also consistent with the sensor measurement. So this is very easy. Now the approximation, since we don't have a physics knowledge of the physics of the problem, we know that this approximation is going to be some map, finite dimensional map. It maps a finite dimensional space to another finite dimensional space. We know that deep neural networks are universal approximators, which is what I just described in the beginning of the lecture. So you replace it with a DNN, okay? And then finally the reconstruction, where you go back to infinite dimensions. Again, this will be a function or a basis of functions. You don't know what it is, so use DNNs. And this is, okay, it's a complicated way to describe this very simple thing. So sensor evaluations use a deep neural network, something called a branch net, to do your finite dimensional approximation and lift back to infinite dimensions by functions. And these functions can be approximated again by deep neural networks. So this is how you approximate the operator. Okay, and there is some other network, PCNet, that I don't have the time to describe. So this is one approach in which you can sort of generalize and you can learn operators by using deep neural networks, because you're only using the deep neural networks to learn the finite dimensional problem, and the projections to finite dimensional lifting you're doing by these different operators. Another way which has been used, again, all of these are like 1 or 2 years old. These are very, very recent papers, is what is called neural operators. So this is a direct generalization of neural networks into infinite dimensions. And the idea is the following. So if you remember, neural networks are compositions, and each piece of the composition, each hidden layer, the input is a vector and the output is a vector. And then there is this affine piece and this scalar nonlinearity. Now, all that we are going to do is we are going to keep this compositional structure. And now instead of having a neural network, we'll have a neural operator, which is a composition of an affine operator and a scalar nonlinearity. So how do you do an affine operator? So this was a vector before, and now it will be a function. So you just replace the vector by a function. This is the key piece. So this was a matrix vector product. Now, elementary function analysis tells us that the right generalization for a matrix in the space of functions is to what is called a kernel integral operator. So this is a kernel integral operator. This is precisely the generalization, infinite dimensional generalization of a matrix vector product. It's also true from spectral theory coming from physics. So this is a kernel integral operator. And now you can parameterize this by a neural network. You can parameterize this by a neural network. This is just what is called a residual connection. I could have also ignored it. So this is your affine piece, translation of the affine into an infinite dimensional object. And then we keep the scalar nonlinearity because this is the best thing that we know. So this is what is called a Nemetsky operator, point-wise evaluation. So these things are called neural operators. And now, of course, there's a kernel. This kernel can be learnable, but the form of the kernel tells you what the neural operator is going to be. And the most popular form of the kernel is what is called a Fourier neural operator. And this has become a sort of a sensation in this field because it's very widely used these days. It's just a different kind of a kernel or different implementation of a kernel. And all of you know this is very elementary analysis, which tells me is that if my kernel is translation invariant, so I have this like this, then the operation, the kernel operation, the kernel integral here is a convolution. And the best way to evaluate convolutions fast in a log linear manner is to use Fourier transforms. You use FFT, a fast Fourier transform, and that's what it does. So what it does is, given an input, it goes into Fourier space. Then it defines the action of the kernel by a matrix, which is essentially the Fourier version of the kernel here. And then it goes back to physical space with an inverse Fourier transform, and it combines them, and this is how it does. So the kernel is implemented through an FFT. So you have to have your inputs on a square grid. And because of that, you can reinterpret this FNO exactly in the paradigm that I had before. So now the encoding is done at these grid locations because otherwise all the Fourier coefficients are given in terms of these grid values or calculated in terms of these grid values. Approximation is done with deep neural networks. And the reconstruction, because we are in a Fourier basis, is done with a Fourier basis. So even though they look very different from each other, at the end of the day, they are more or less the same story. And why should this work? So now you're solving a formidable problem. You're trying to approximate an operator, right? And it turns out that you can do this. So there's a more or less comprehensive theory now in these papers. A couple of them are already published. One of them is coming upstream. And the first thing that you do is, just like I spoke before, neural networks are universal approximators of functions. Neural operators are universal approximators of operators. So they have exactly the same sort of approximation power that neural networks has. I mean, this is sort of surprising, but it is true. But more importantly, we have a lot of quantitative information. We have bounds on both sides. I don't have the time to go into details, but because you have an infinite dimensional problem, so you can prove that the size of your neural operator will scale like this. So it depends on the regularity of the map that you have. But more importantly, it depends on the number of sensors, because this is where the infinite dimensional input is sort of driven down to finite dimensions. But remember that at the end of the day, it's an infinite dimensional problem. So this guy is going to go to infinity. As epsilon goes to 0, it's a 1 over epsilon. So it's infinity to the power infinity. So you have this curse of dimensionality again. So these papers are very long papers, and all the effort is spent in saying that, okay, for a generic operator, indeed, or a continuous operator, you would have this curse of dimensionality. This is not a solvable problem. However, when your operator comes from PDEs, we have some special structure, we have a bunch of special structures. So for all these PDEs, which represent the whole spectrum of PDEs, one can prove that these objects, they break the curse of dimensionality. So they are going to approximate these PDEs rather efficiently. And there is a unified framework in a recent paper, but I don't have the time to explain this. So I'm more or less coming to the end of my talk. So just as a numerical experiment, a very simple numerical experiment, because there's no time to give you detailed numerical experiments. So here's a force pendulum, just an ODE, but the simplest ODE that you can think of. We have a time-dependent forcing, which is my input. So it's a function. My output is going to be the displacement, so which is the angular displacement in this particular case, which is also a function, time-dependent function. So here's a typical input, here's a typical output, and my functions are given from Gaussian random fields. So I can draw samples out of that. And you can see with all these three architectures, more or less, all of them worked well, and they were able to approximate this. Also, you see that visually. They were able to do a good job at approximating this. And you can do this, means people have done sort of industrial scale problems, weather forecasts with FNOs these days, but it's not my work, it's some other people's work. We just proved that this indeed can be done. Now, in this data physics landscape, some of the major limitations have been removed, and we are somewhere here. We're still not there because we don't use the physics in any particular manner here. But this is not to say that this is a solved problem. There are several issues with this, but maybe for the sake of time, I'm going to sort of cross over and not describe this. Okay, so one of the issues is that if you have limited data, then you have some serious issues. Means what do you do in that case? Because these require a lot of data, because these are infinite dimensional objects. So what you can do is that you can combine the second part of my talk with this. You can combine pins with operator networks. And then there is what are called PNOs, or physics-informed neural operators. And there is a complete theory for these. These work well in practice. And in this data physics landscape, they are coming closer to this. They need some physics and less data than neural operators. And we are heading in the right direction, but we have not reached the end goal. So perhaps it's a good time to summarize, because I'm running out of time. So traditional numerical methods are physics rich, but they're expensive. So you can't really use them in the sort of problems that we want to do. So you need to use data in some manner. If the problems are parameterized and there's a lot of additional domain knowledge available, you can just use supervised learning. It does not use any data. And if you use certain tricks, this can be very, very effective. If you don't have that, if you don't have a lot of data, and your traditional numerical methods fail, you can use PINs, physics-informed neural networks, for both forward and inverse problems, and they are very, very effective, but they need complete knowledge of physics. If you have only partial knowledge of no knowledge of physics, and you don't have parameterizations, you are in this domain here. If you have some physics, then you are in this domain here, but we have still not built sort of a universal system where we can sort of go between data and physics in a sort of a neat manner. this is still very much, and there are many, many issues, particularly here, because these are very, very recent architectures. So there is still a long way to go that we can just replace traditional numerical methods with sort of data-dependent machine learning methods. But at least the process has begun, the journey has begun, and it's quite exciting. So thank you very much for your attention, and I'm sorry for running out of time and not showing you some of the slides. Maybe in the discussion, we will come to that. Thank you very much.
Thanks, Sid. That was a really nice talk. If there are any questions, just please unmute your microphone and ask the question.
Hello, I have a couple of questions.
Please.
Have compressive sensing ideas been used here at the encoder level? For example, if you have some reason to believe that the solution is sparse in some basis,
Yes.
you could bridge that.
Yes, absolutely. Means you could use compressed sensing, and in fact, you could, for instance, in the encoding part, you could use. In fact, what we use is a slightly dumber version of it, which is to use PCA, principal component analysis. So many physicists also know this, that when we have a signal, we can extract principal components out of it by just using the covariance matrix. And then you can indeed use that, and there is also, means it's also quite effective. The problem with compressed sensing possibly is, that it only works under certain assumptions, like you have the restricted isometry property and so on and so forth. Many of the examples that I'm giving you don't have that sparse structure. So it is unclear if it will be very useful. But when it is having the sparse structure, you can, and people have used different kinds of, anything can be used at the level of this encoder. So in particular, you can use compressed sensing. I think this has already been done by some people at the University of Pennsylvania. I saw some, but this can indeed be done. But I would still say that it is rather restrictive because of the restricted isometry property that is there. So you won't have the sort of generality that is available. And you said you had a second question, so please.
Yeah, the second question was prompted by Vishal's question. So in image processing, there are the explicit cost functionals where you allow for discontinuities because the edges, so you smoothen sort of parallel to the edges, but not across them. So is that kind of thing attempted here where you expect discontinuities?
Yeah, when you expect discontinuities, there are different ways of dealing with them. So I didn't have it in my slides, but I actually can show you. Maybe I have some other slides, so I can, why is it? Okay. Yeah. So let me just show you because I have the slide right here. So this is a classical case of discontinuity. Maybe I can also go to full screen. So this is a classical case of discontinuities, right? So for instance, you have the Burgers equation, right? And then when the viscosity is going to be finite, you have excellent approximation, but everything depends on the viscosity. So it blows up and it doesn't work. So one way to fix it, there are different ways. One way to fix it is to do this entire residual process in a weak manner, okay? So what it means is that instead of having the derivatives on the function itself, you move the derivatives onto a test function, like what we do in finite elements, for instance, right? And now, if I don't want to use meshes, because I didn't tell you that, but pins did not need any mesh, I could just use random points. So then this guy will be a neural network, but my test functions also will be neural networks. So you have to maximize over the test function space, and you have to minimize over the sort of trial function space, and you have to solve this min-max problem. So you have to use what is called adversarial training, which is used, for instance, in GANs, generative adversarial networks. And this works. There is theory, there are experiments, but it's expensive, because you have to do this min-max, so this is expensive. So I think these kind of ideas are already there, means we have papers, some other people also have papers. And your idea was to sort of use a loss function that essentially sees the discontinuity in a special manner.
So, yeah, so usually in image processing, you can put something like an L1 norm on a derivative.
Yeah, that is not going to work. At least in this particular setting, L1 is, or PV norm is what is used. That is not going to work. And the reason for why it is not going to work is because the strong residual blows up. So nothing. So at best, you can evaluate the residual in the negative Sobolev space or in a measure space or something like that. So there's a deep mathematical reason why it doesn't work. So it is sort of.
So what kind of loss functions can we do if I'm thinking of Sobolev norms? I
So
saw
this is-
mostly
this
L2.
This is a H-1, for instance, or a
Right.
W-1. So this is
Right.
precisely a loss.
Got
It's
it.
not equivalent, but it is almost equivalent to a negative Sobolev space norm.
I see.
And this is why it sort of works. There is a complete theory in a paper which should be available in the next 1 week, and we do numerical experiments. But it's sort of, I'm afraid that it might not scale because the training process is very expensive. Your min, max. So it's sort of very expensive. So I'm not sure if this is the right way to do with discontinuities. By the way, in the radiative transfer, which is a linear problem, okay, now I'm changing slides. We could approximate discontinuities, but this is linear. So there is no propagation of the discontinuities. This worked very well, even with a plain vanilla bin. Because you just smoothen, and if you can smoothen, and if you're close to the discontinuities, close to the smoothening, then it works. But in a nonlinear problem, you can't guarantee that anymore. So that's the reason why it doesn't work.
Professor Borka, were there any other questions?
Let me just comment on this image processing part again. So there are a couple of, long in 90s or maybe sooner, there's some works which did the following. So this work by Perona and Malik.
Yes, absolutely.
Yeah, you are aware of it. They just put a diffusion coefficient which depends on the gradient, and so that don't smoothen across the edges. That was one. And the other one was Mumford and Shah, where they actually put explicit penalty on some putative edges, and also that's part of your optimization problem.
I agree. I'm fully aware of these papers of Perona and Malik and Mumford and Shaw and so on. I still believe that they are not going to work because, first of all, they work well in image processing because you have one sort of fixed or there are fixed discontinuities. Right now we're dealing with moving discontinuities because my discontinuities are going to move. So it becomes very difficult to sort of penalize, and people have tried, for instance, to use the total variation norm, which is roughly Perona-Malik, and this didn't work. And the reason, there is a fundamental mathematical reason why I believe that this doesn't work. But for sure, I don't know if someone has tried the Mumford-Shaw explicit penalization approach, but I would still be surprised if it works because it doesn't take out that mathematical difficulty that the error is going in a strong norm always is going to blow up. So if I had pen and paper, I would explain it to you better. But I think there is a fundamental issue, at least with this nonlinear problems, why it doesn't work.
Okay, thank you.
Yeah.
I see somebody has their hand up, Jack Kumar.
Yeah, hello.
Yeah.
Can you hear me?
Yes, I can.
Okay. So most of the problems that you have described right now, they seem to be like function approximator, building surrogates, surrogate methods. And to some extent, you discuss this discontinuity problem. But if I were to try to capture finite time singularity, as in Navier-Stokes equation problem, how would you go up? So we still don't know how to write a numerical scheme which doesn't have any artifact. But do you think neural network based surrogate might be able to capture it? Because it looks like even if it does, how do you go about proving such a giving arguments as to why this method would work? What kind of proof would you need to go about solving such a problem?
So if I knew the answer, I wouldn't tell you, right? I would claim the $1 million myself. But jokes aside, this is, I think that would be very, very hard. I wouldn't use neural networks to try to capture the singularities of the Navier-Stokes equations. Means this is, because even with traditional numerical methods, it's very hard. Even if I have all the computational time in the world, it is still very hard to sort of capture discontinuities and singularities and so on. And in this kind of a method, anyway, you need data, right? Means it's sort of a data-based, or if I don't use data with pins, I'm certainly not going to be able to see such fine features. Neural networks will not be able to see discontinuities, at least the ones that we have, which are sitting on a sort of a a set with a very small Hausdorff dimension, so this is where, so we expect the blow up to happen in very, very tiny sets, right? Means possibly even points, means the Caffarelli-Nirenberg estimates are, I don't remember, but something around 0.7. So it's not even on a line. It has to be on a point or on a Cantor set or something like that. Means I wouldn't do that with neural networks, let alone prove that once I see something, means no, I wouldn't. And if someone shows me that, I won't believe it, because these are meant for more regular sort of structures, So just imagine you have such a, forget about, let me try to produce some data where there's something is blowing up on a Cantor set, and let me try to understand that or try to learn that with a neural network. Means this will be very, very difficult. I don't know what sort of, it's a measurable function. So in principle, yes, you can approximate it by a neural network. However, with that kind of lack of regularity, with that kind of singularities, it will be formidable. The problem will be formidable, and I don't see neural networks will give you a better answer that way.
So what makes it feasible to work with the shocks in comparison? Why is it that
it is a very, very good question, right? So if I just write math, then it is not very useful. But the point is, okay, let me even do the, let me show you the two-dimensional problem. So that, okay, let's go to this. Okay, so think of it, okay, if you want to think of it in terms of functions, then I can give you a proof, but that doesn't give you the intuition. But look at this just as an image, okay? So if you think of it as an image, this is not a very, very complicated image, right? So in terms of an image, I just have this leading edge shock here. I have something smooth happening. I have some little bit of smooth features here and so on. So in some space that I don't know mathematically how to describe, I can break this down hierarchically by first I learn the shock, then I learn some, and it's just one discontinuity, means how hard can that be for a neural network, means they can easily work with images and so on. So just in terms of just intuitively, it's not so hard to learn this, right? You can just learn this intuitively. That's why the neural networks sort of do well here. I can write a proof, but this proof is not sort of, means it doesn't tell you more than just looking at the image itself. However, means now now this is a different talk, right? Let me go back to my original talk. This is a very, very important question. So shocks by themselves are not, why is it not working? Shocks by themselves are, for neural networks, are not a hard object to approximate. However, if you go back to my very first slides when I had this very complicated turbulent flows, yes. Now just imagine this is no longer, okay, even if you have a shock, means you have much more complicated things happening. Just imagine as an image, to just hierarchically represent it in some representations in some latent space is much, much harder. I don't know the math. No one knows the math on how to sort of talk about this. What is the right sort of function spaces to talk about? But this image, to learn it for a neural network is going to be much, much harder. So at the moment, there is no numerical or no neural network-based method, machine learning method that can learn a function like this, let alone something like this, So I can learn many things, but these are based on sort of either smoothing, or let's say that the amount of features that are there are, let's say, rather nice. If I have lots of multi-scale phenomena, lots of different features, I don't know yet. I'm hopeful because there are machine learning architectures out there which can do this. But at the moment, it means we are not yet at that place. Whereas a traditional numerical method can do it. It costs me a hell lot of money and time, but it can do it. And it was not able to do it when I started when I was a graduate student. To do this simulation would have been impossible. Right? It was simply impossible. I couldn't do a three-dimensional simulation. Today, in the next generation of GPUs, which we are buying in the Swiss Supercomputing Center, we can do it on a single GPU. So computing is also with traditional, so things, not because we have made big advances with algorithms, right? The computing power has become better. So, but I think with neural networks, we need new algorithms. Whatever I just described might not suffice for these very, very complicated flows.
Okay, sure, thanks.
Perhaps while we're waiting for somebody else to ask a question, I'll take the prerogative to ask you another question.
Please.
So, there are a number of people here who solve PDEs for their research, right? So I guess the question is, what's the cost in terms of researcher time to sort of port my code that I've developed in, either finite volume or spectral or whatever. And now say I want to use these tools, presumably the code has to be rewritten, revalidated, so on and so forth. So
actually, yeah, so there are, first of all, not a lot, means because, there are two settings that you're in. You're either supervised or unsupervised, right? So if you're supervised and you are in sort of in a complete sort of a parametric setting, you can use very standard plain vanilla neural networks to do it. If you're unsupervised, all the unsupervised algorithms out there, pins and so on, are very, very easy to code. So the basic starting barrier is very low. Okay, because mostly codes are available. If you want to use FNOs, you just download the code. They have a very good code from Caltech, and you just use that. Means it's mostly that is not the barrier. The difficulty with machine learning is there's a lot of engineering which goes in, and the engineering comes from here. So remember that I'm trying to solve a very complicated nonlinear optimization problem, right? And now this, I wish I had in my course, I try to show some of these loss landscapes. They're very, very, very sort of funky, so you can be stuck in local minima and so on and so forth. So it requires a little bit of instinct and understanding to sort of train these neural networks well. If you are really good, then Google hires you for $1 million, right? So this is sort of, it really requires some instinct and some engineering to be able to do it. So when I tell a master student to do it, it's not super easy. It takes them some time about what sort of parameter. There's a lot of hyperparameter tuning. And this is primarily because I have this non-convex optimization problem and I'm solving it with stochastic gradient descent. So I don't have very good, so this is where statistical physics in particular might play a role to understand this, and people have tried this, right? To understand this loss landscape better, because at the moment we don't have much of an idea. So that is the barrier. The barrier is not the fact that the starting point is low, but to get good results is not trivial because of this element. So I might prove many, many theorems, but at the end of the day, you have to do this process. You have to solve this nonlinear optimization problem. And this part of the error, no one knows how to bound. Or the bounds are very, very weak. They're based on some linearization, some neural tangent kernel, and so on. So there you need to build up expertise in the lab and so on and so forth. And that takes time. That's why they are not as easy to use as, and the same sort of neural network architectures that work for image or text might not work in this context. So one has to sort of spend time. So it's a resource to have a well-trained PhD student who can train these neural networks and get you state-of-the-art results. You don't want to lose them, but then Google pays them well, so you can't keep them. So it's so there is a practical element there. Yes.
I see. Any other questions?
Just one last question. Maybe.
Please go ahead.
Yeah, it's not pertaining directly to your talk, but there is a class of nonlinear partial differential equations of general relativity, which people in the last 10, 15 years have learned how to solve. And they're very difficult problems, for example, of black holes colliding. And do you know whether these methods are being used by the practitioners of that art?
Yeah, I think they want to use it. I actually know some of the people who do this sort of large-scale black hole mergers and so on and so forth. So these are, I also know quite a few people at the Albert Einstein Institute where these codes are developed. I know them rather well. They are a bit skeptical because the reason why they're a bit skeptical is because they think that their problems are sort of too complicated at the moment to use these methods. I don't think so. I think their problems, whatever they do, they see still black holes, right? So if you just think in terms of feature representations, these are large scale features which are coming together. So in principle, it's like two vortices merging and coming out. So I don't think they're as complicated as what I am trying to do. So I have told them that maybe they should. I think there is a lot of interest and investment, but I think in astrophysics, people are mostly using it from the sort of data side. So they have some data and then they want to filter the data. They want to make predictions on sort of a pure data regime, not on a pure physics regime. But I don't see any reason why we can't use these methods. And anyway, these methods have just been sort of started to be developed, right? So reliability is still an issue. It will take time, but I'm pretty sure that those methods they have hand engineered. These are very, very complicated codes. They have used a lot of, and it's I know at least in some groups there are only 2 or 3 people who can run these codes. Not everyone can run them because they have a lot of sort of design features. It will take a long time, but I think eventually those problems will be solved by these methods. They are also relatively smooth compared to shocks and so on. So I believe that it can be done. And if you don't have to generate meshes, you don't have to sort of isolate time-like and space-like singularities, if you can do that. Yeah, if I knew enough general relativity, I would do it myself, but I let some other people, I have some friends who do this and I've been telling them, try this out, but at the moment they're a bit gingerly about this, but maybe that will change in the future. There is a question in the chat, which I can sort of read through. Oh no, it was from Rajesh. Okay, just a comment. Yeah.
So Vishal, can I ask a question?
Yeah, go ahead, Amit.
Yeah. So one kind of roughly following up on your comment earlier to Vishal's question. So the traditional numerical methods and so on give you a, so say, constructive way to bound these errors that you make, and hence find ways to improve upon the method.
Yes.
That is that something that comes out of existing theoretical results?
Yes.
Ways to improve. So if you're making certain errors, how do you make them better? Or
so this is a very good question. In fact, this paper that this was paper some years ago, where my whole point was exactly this, that I viewed a traditional numerical method as having some tunable parameters. Whether you express it in terms of neural network or not, there were some tunable parameters. And then I asked myself the question in the paper, if I use data to determine these weights, how much of a benefit do I get? And indeed, I was getting huge amounts of benefit. And the reason why I did not sort of, in some sense, I'm pursuing theoretically, this is what is going on all the time. So all these proofs here, so as you can see, that's why I sort of motivated operator learning in terms of traditional numerical methods, because these are nothing but sort of fancy ways of data-dependent ways of traditional numerical methods. So all the proofs here, for instance, all the proofs, they're based on emulation of a numerical method. So for instance, you take Navier-Stokes, you have spectral methods for Navier-Stokes, and all that I'm showing is that the Fourier neural operator is just sort of, I am able to reduce the Fourier neural operator to such an extent that it simply learns weights in the spectral methods better than just collocating the spectral method. So this is how the proof works. Okay, the proof works exactly like this, and that's why I'm able to break the curse of dimensionality. Otherwise, I wouldn't be able to break the curse of dimensionality. However, in terms of implementation, one rarely implements it like that. It is true that these methods can be seen, because what happens is that then you won't get, in terms of resolution and so on, you don't want to start with a very, very fine grid, for instance, right? Then the architectures become very, very big. So you want to sort of randomly search the whole search space, and hopefully you will get even a better minimum than what you had before. So people are not, so there is a hybridization which is possible between these and traditional numerical methods, which is also being investigated in my lab, but also elsewhere. But indeed, the proofs are completely based on reducing them to traditional numerical methods with dependent weights. If you read my paper, that's what you see. But that's what I know. I'm a numerical analyst, so I could reduce it in that way. But I'm not convinced yet that that's the practical way of getting the best weights, or I just do a random search is the best way. I still think the latter.
Okay.
Because these loss surfaces are so complicated that you might be at a very, very bad loss surface. So then you can only do worse if you start with the weights of a traditional numerical method. Mm-hmm. So this is the concern, right? Because of the optimization problems.
Yeah.
Any other questions? Spencer?
No, it just.
Okay, I guess there are no further questions. Siddharth, thanks again for a wonderful talk. It's very illuminating.
My pleasure. My pleasure. And the slides, I can send you the slides if someone is interested, because I did not cover quite. I ran out of time very easily. But
Right. Yeah.
okay.
Okay.
That
Thank
would
you.
be fantastic.
Please visit
Thank you
us.
so much.
Please
Yes,
visit us.
I will certainly, the next
Let
time
us know.
I'm in Bangalore, I will come to ICTS. So it's.
Thank you so much. Yeah.
I will do that. Thank you very much for the invitation, and I'm looking forward to meeting all of you.